Okay. So I only to speak something about the homework, and then we continue the lesson. Okay. The first is about the simple but not Z module. So it's very simple if we can take the vector space. And the vector space, you can, for example, very simple, that is, R is the R module. And you know that is the dimension is, the dimension of this one is equal to 1. And 1, and so that is simple because 1 uh, mean that there is no submodule here. The dimension 1 is that is only have the submodule is R and then is 0. So that is very simple. Here I can say that the R square and divide R, that is the similar, because that is the isomorphism to R. So so that is very easy if you take a many vector space with dimension 1 vector space with dimension 1 is simple. So that is very easy to take many. Okay. The second is the B here is here is the first we on to write the decomposition of a number to the prime. Okay, so here is 24 is equal to 3 and 2 power 3. So power 3s, and then some people late here. Đoàn Nguyên Hành. I will stop here. Okay. So so in this case, you can know that the divisor of 24. So you can take a divisor of 24 is here is 24, 1, 2, 3, 4, 6, 8, and 12. So you have the maximum submodule here is 3s as equal to Z24. And maximum is here. The submodule is many people, I think that can do it try. However, when you take the max and minimum, some people try and not try. Mean that you can see in the diagram the 3s and 2s is maximum because there is no here, and 0 is here is the 12s, and 8s is there is no submodule here. So you can see here is minimum and here is the maximum. Okay, so but some people Oh, sorry. Here is maximum. Okay, here that is only 2 because the 1.2 you have the 32, so that is equal to the 2 power 5. So the maximum is here and minimum is here. Okay. And the last one is only checking. The first is checking each axiom. So many people forget to say that the I power n and with plus is abelian group. You should say about this. And then this one, this one, this one, and this one. Here is abelian group, and then 4 is here. You should check this one. For example, I write one of this here. Okay, you can. Here is one example. You should check all of this. And for the submodule, here is a submodule. So that is very easy to checking 3 condition. The first condition is here, the second is here, and the third is here. So I check one example is here. So that is very easy. X is equal to sigma here. Y is equal to sigma here. And then X plus Y is equal to sigma here. So, but if you carefully, you can divide, for example, the X is mi, xi, with I in equal to 1 to n, and Y is equal to the sigma, the mj and yj or xj prime. J is from 1 to m, something like this. Here m maybe s. And then you can divide two kinds. Some xi is equal to the xj prime, something like this. So you can take the elements of okay, sorry, here is m. Okay, m. You can divide it something that is mi and mj is equal to. So you can, so for example, the mi is equal to the mj. So you can take the mi here, and here is the mi plus xj prime, something like this. So, but any case, you can write the x plus y is equal to the sigma plus sigma is enough, because that is belong to mi is enough. Okay, so that is only checking. So I think that you should do many homeworks for familiar with the homeworks of our subject. Okay. So I will. So I send you. So you should read it carefully. Now I continue to say about the sum of submodule. For easy, I will say about the 2 submodule. Okay, that is more easy. So I say only 2 submodule. For example, M1 and M2, that is submodule of MR. So, okay. So we write M1. We have a definition of M1 plus M2 is equal to the what is that is equal to the M1 and plus M2 with M1 in M1 and M2 is in M2. We define this thing. And we call that is the sum of two submodules of MR. We say that that is the sum of two submodules. And we have the from the definition here, we have the proposition. We have the proposition. The M1 plus M2 here is a submodule of MR. Is the submodule of MR. It's very easy to check this. To check. The first is M1 and plus M2 is not equal to the empty set. Since you can write 0 is in M1 and plus 0 is in M2 is equal to 0 is in M1 plus M2. So that is not empty set. Here is belong to M1, that is belong to M2, so that is belong to M1 plus M2. Now we take the X in M1 plus M2 and Y is also plus M1 plus M2. So you take the X plus Y is equal to, for example, X is equal to, sorry, set X is equal to the M1 plus M2 and Y is equal to M1 prime plus M2 prime. And then you take the X plus Y is equal to M1 plus M2, M1 prime plus M2 prime. And you remember that M1 is in M1. M1 prime is in M1. So M1 prime plus M1 prime is, this belong to M1. And this belong to M2. So the sum is belong to the M1 plus M2. So you take the X is in M1 plus 2 and Y is in M1 plus M2. So the X plus Y is belong to the M1 plus M2. Okay, the second condition. And the first condition is XR is equal to the M1 plus M2 and then tie with R. So that is equal to the M1R plus M2R. And that is belong to M1. That is belong to M2. So that is all is belong to M1 plus M2. So we have the conclusion because that is the third condition, the second condition, and here is the first condition. So you have the proposition is sum of two submodule is a submodule of MR. Okay. Now, okay, so that is my proof. I erase. Okay. So we have the definition sum of two submodule, and then we prove that M1 plus M2 is a submodule of MR. The problem is, you remember that I said to you that the union is not the submodule of MR in general. So because that is the not the submodule, so we will take the M1 union with M2, and then we take because that is not submodule, so I will take the submodule generated by M1 and M2 union with M2. So what happened? It will be equal to M1 plus M2. Okay, that is very nice result because we have the sum here, but the sum is generated by the union of M1 and M2. Okay, so you can see something like this. Here is 0 is always belong to. So that is, for example, the M1, that is M2, that is M1. So you have the union of M1 and M2, something like this. I will draw something like this. Okay, that is M1. But you know that the M1 union of M1 and M2 is not a submodule of MR in general. So we will take the M1 plus M2, something like this. Okay, so the M1 plus M2 is equal to the M1 union with M2, and then the generated. So to take the generated, so that is equal to the M1 plus M2. Okay, so that is very I will take the example. You can see very clearly about it. But the first, we would like to prove this. Okay. So for proving this, if you want to prove the generated here is equal to here, so you will prove the three steps. The first step, you prove that M1 plus M2 is the submodule of MR. That is already here. The first step is already, okay? The second is you prove that the M1 union with M2 is the subset of M1 plus M2. Okay, I will prove it. I will prove because you remember the definition of generated. That is the smallest submodule containing. Okay, you remember the S is is equal to n, then n is the submodule of n containing s, and n is a smaller containing s. That is definition. Okay, I don't recall it again. So M1 is, so you take the X is in M1 and then union with M2. So it will be X is in M1 or X is in M2. If X is M1, so you write X is equal to M1 here. So X plus 0. Okay, it's in M1 plus M2. Because you write here is X is here and 0 is here. Okay, so, okay. And X is M2, so you write X is equal to 0 plus X. 0 is in M1 and X here is in M2. So that is belong to M1 plus M2. So all the case, X is here is belong to here. So you have this is the subset of this one. That is the second. Now I will prove the last one. I will prove the smallest. Now let's n be a submodule of MR containing M is in N. We will prove that M1 plus M2 is the submodule of N. Mean that if you take N is containing M1 union with M2, and then M1 plus M2 is smaller than N. We will prove this one. Okay. So I will take one element of M1 plus M2. So for X is equal to M1 plus M2 belong to M1 plus M2. M1 is M1, M2 is M2. So M1 is M1, but you can see here, M1 union with M2 is in N. So M1 is in N, N, and then that is in N, that is in N, so plus is in N. So this will follow X in N. So all element here is in N, so M1 plus M2 is a submodule of N. So we prove that, we already proved that the M1 union with M2 and generated here is equal to the M1 plus M2. So I have the definition of M1 plus M2, and I already proved that M1 plus M2 is the submodule of MR, and then we prove that M1 union with M2 is equal to the M1 plus M2. Okay. So for the case 2 submodule, I have already proved, but uh, in our book, you remember that we should have the sum of many, not only finite, but that is okay. Here you have the definition of 2 to 10. Okay, now I extend to the infinite scale, infinite, infinite, infinite number of submodules. So what is the definition? The definition is the sigma of mi with I in I. That is equal to the many the sigma with I in I prime ai, and I prime is the subset of I and I prime is finite. Okay, so I would like to explain this, and then you can understand the extension of infinite. Okay, when you have the M1 and M2, that is equal to the M1 plus M2, and then M1 in M1, M2 is in M2. It's easy. Okay. And then you have the M1 plus M2 plus M3 is the same. M1 plus M2 plus M3, and then M1. Okay, Mi is in Mi, I is equal to 1, 2, 3. Okay, so on, many. Very easy if you go to M1 plus M2 plus 2Mn. But it's very easy here. But if you extend to the infinite, that is not easy, because you remember that in algebra we don't have the sigma of for example xi is I from 1 to infinite, or sigma xi is I in any set. We don't have the sigma here in algebra. We don't have uh, the epsilon and delta. We don't have this one. It's in analysis. So to use the epsilon and delta, you can define the limit, and then from the limit you can have the definition of the series of the, okay, that is congruence, okay, something like this. But in algebra we don't have this one, so we should use something like this. Mean that we can take a sigma ai, we write same as, for example, when you can, if you, that is one of the method is to write here, or the method is to write something like this. Something you can write that is, you can write that is a sigma ai with I9. However, ai is equal to 0 for all except a finite number I9. is equal to something like this. Equal to. So the first is to write is finite, and the second is to write infinite. However, that is on only finite. Because in algebra we don't have the sigma of infinite number, infinite elements. So you write something like this. Because something that is difficult, so I will say something in Vietnamese. Như vậy là tôi chỉ là tôi dạng từ M1, M2 là hai module con của đó, rồi tôi cộng nó lên. Thì đến MN thì cũng dễ dàng thôi, tại vì là M1, M cộng M2 cộng cho đến MN thì lấy các phân tử của nó cộng với nhau. Ví dụ M1 cộng M2 cộng cho đến MN nhỏ. Đấy. Mỗi MI là thuộc MI hoa. Nhưng mà khi lấy tập đó là tập vô hạn, tức là tập Y này là tập vô hạn á, thì vì trong đại số là không có khái niệm epsilon và delta, để cho là từ epsilon đến delta chúng ta có khái niệm giới hạn. Từ giới hạn này chúng ta sẽ có các cái tổng liên phân, đúng không? Sigma xi về y đi từ 1 đến n, rồi xong rồi mình cho cái này là si chẳng hạn, rồi ta sẽ lấy cái si này tôi sẽ cho ra vô hạn. Thì cái này là ở trong đại số không có, thì người ta mới chừng thì những cái sigma như thế này cũng đủ để khảo sát trong đại số, mặc dù nó hạn chế. Tức là viết thì có vẻ vô hạn, ví dụ như viết cái dưới này là có vẻ vô hạn này, sigma tất cả các ai với y đi từ 1 y thuộc y thuộc y, mà y này có thể vô hạn. Nhưng mà cái câu đằng sau kèm theo là gì? Là AI này bằng không hết tất cả for, ngoài trừ một số hữu hạn y thuộc y. Như vậy là viết như thế này thôi, nhưng thực ra là chỉ có một số A, y là cả không thôi. Còn phần lớn là đều bằng không hết, ngoài trừ một số hữu hạn đó. Ngoài trừ một số. Thì đó là một cách viết thứ nhất. Cách viết thứ hai là viết sigma I về y thuộc y phẩy, với y phẩy là hữu hạn đấy. Cho nên cái sigma này thực chất là nó vẫn là hữu hạn. Cái sigma dưới này viết thì vô hạn thế này, nhưng thực chất là hữu hạn. Và ta lấy như thế này đủ để khảo sát, và ta gọi cái này là tổng sum of mi with I in I submodule of MR. Okay, that is the sum. And the sum here is we prove that is the submodule of MR. And the union of MI with I in I, and then you take the generated, and then that is equal to the sigma of MI with I in I. So that is the homework you should find in my my course, my textbook. I already drew here. You remember to read it. Okay. So that is a proposition 229. So I have a proof here already. So you should read and understand it. That is the sum of the submodule. So Okay, so now I go to the end of this section, that is equation module. Um, the equation module. Now let's MR. And we take the N is the submodule of MR. Sin M and plus is an M over N, and then plus here is an abelian group. Is an abelian group. You remember that is the Quotient group. Quotient group. And you remember the operation here for M in M and then plus N, and then you plus M prime plus N, that is equal to the M plus M prime and then plus N. For M, M prime is in M. Okay. That is the knowledge that you already study in R plus algebra 1. So from the abelian group, you can construct the abelian group, that is a Quotient group, M over N, and the operation is here. So now if you want to have the Quotient module here, the Quotient module here, if you want to have the Quotient module here, you will need another operation, is the module multiplication. And then now we have the theorem here. Let M is something like this. Okay, let's is a submodule F and MR. We define the M over N, and then we tie with R here to M over N. And then that is M plus N, and then is R in R. And then we say that that is M plus N, and then times R. That is equal to the MR plus N. Then, for example, I say that is a point. Then point is a multiplication, module multiplication. multiplication. Okay, so I establish a new operation here, and from the multiplication here, we have for example, here is A, and then B is M over N is right R mode. Is a right R. Okay, we can prove it easily. The first is proof A, because you can see that here is M plus N is equal to the M prime plus N. Then you will write N is belong to N. And then you will tie R is belong to N. R minus M prime R belong to N, and N is equal to M prime R plus N. So, and then this is equal here. So, two class equal, and then the result of the point here is equal. So that is operation. That is operation. That is. And the B is you check the M, N, and Plurian group is already. To prove more for axiom, mean that the M plus N, and then you tie with R, that is should be proved the M plus N, and then R plus M prime plus N and R. M plus N, and then plus R, and then plus R prime is equal to M plus N plus R prime here. Okay. And then M plus N, and then R plus R prime is equal to the M plus N R here. And then M plus N R prime here. And the last one is M plus N, and then tie with 1 is equal to the M plus N. You should check for axiom here. And I can check one of this. For example, okay, what this? Maybe for example here. Okay, here you can write M plus N, and then R plus R prime. Okay, that is equal to the M and R plus R prime, and then plus N, and that is equal to the MR plus MR prime plus N, and that is equal to the MR plus N plus MR prime plus N, and that is equal to the M plus NR and plus m plus n r prime. Okay, that is we need to prove. We need to prove. So so from this we have the definition of the mn in this theorem is called equation. The equation module of m over n. The equation module of m over n. Okay, we have 10 minutes rest, and then after this, I will give you some example about the sum of submodule and also the equation module. Okay, we have a rest. Okay. Okay, I hear some people come, but we cannot back. So I recall that after 7 o'clock, I should open the whiteboard. So when people come, I cannot come back because the lost the time of many people. Okay?
Okay.
I have some people have responded. I don't remember who.
Thầy
Nói đi ạ.
thầy cho em hỏi thầy là khi mình học về cái nghĩa về module này là có bốn cái điều kiện để cho cái nhóm Abel mà trở thành một cái module này. Là cái điều kiện thứ tư này là ví dụ như là x nhân 1 bằng x hoặc là 1 nhân x bằng x này. Thì cái phần tử 1 của thầy, phần tử 1 nó là cái gì thầy? Ví dụ như là
Một là của văn, một là của văn,
một là của văn, nhưng mà văn nó là kêu là không nhất thiết phải có đơn vị mà thầy.
không, văn phải có đơn vị. Tất cả văn của mình là phải có đơn vị. Nhá, mình nhớ là văn của mình là có đơn vị nhá.
Dạ.
Cho nên chi là nó mới chia ra là hai loại. Ví dụ như là không gian vector vậy là nó có unita vector space và non unita. Thì bên module cũng vậy. Nếu như văn không có đơn vị thì người ta định nghĩa là non unita. Còn của mình là cái tiếng đề cuối người ta gọi là unita. Unita là unit đấy. Thành thử là nhớ rằng là trong cái sách thì trong cái câu đầu tiên của tôi là we always assume that the ring is have the identity one is not equal to zero mà.
Dạ, anh thấy rồi.
Ok.
Dạ.
Vừa rồi ai mới đến Đoàn Nguyên Hành đúng không? Hành mới đến đúng không? Khi hồi nãy tôi có trở lại tôi làm một lần, nhưng mà như vậy thì cảnh gì thấy là mất vài phút. Hành đâu rồi? Nguyên chứ không phải Hành. Đoàn Hành Nguyên. Đúng rồi. Đấy, đây Bảo này, Bảo vào trễ quá này. Ngầm vì là học online cho nên bảng cũng như vậy, là mỗi lần là phải quay trở về rồi rồi cho phép rồi thì lại đấy nó mất thời giờ của người khác, cho nên gì là anh chỉ nhớ là phải đi đúng giờ bằng cách là cái gì mở máy tính đó chứ có gì đâu, chứ có phải là chạy từ cổng trường chạy vào đâu mà trễ 5 phút. Tôi là chỉ sợ mất thời giờ của mọi người và nó giảng đoàn đấy đó. Cái gì sau này cái gì đi đi dạy là cũng thế thôi, mọi người mình đang giảng là tự nhiên là có người là nói cái này nói cái kia là tự nhiên mình bị ngưng đi, rồi sau đó cái mặt nó trở lại là mất đi cũng tối thiểu phải nửa phút, anh xin là khoảng 30 giây rồi ta nghỉ đi. Ờ, Okay, now I give it two example. The first example, now I take a 2Z, is the submodule of ZZ. And I take 3Z, is the submodule of ZZ. Okay, I can draw it here. So that is 0. And 2Z, that is, here is 1. And here is 2. And here is, okay. I will write the 2Z. 2Z is here. 2Z is here. 2, 4, 6, and also 0. That is all of the even number. So on. And also minus 2, minus 4, minus 6, so on. Okay. The red is 2Z. Because 2Z is 2 and Z in Z. 2 and Z in Z. So that is 2, 4, 5, 6, 0, minus 2, minus 4. So on. Okay. And 3Z. 3Z is, of course, 0. 3 with 0 is 0, so that is a 0. Is 0. I write here 0. And 3. Six. Okay, here. 9. So on. And here, minus 3, minus 6, so on. Minus 9, so on. Okay? So now you take the a 2Z and union with 3Z is equal to, okay, that is 2Z union with 3Z. You can take the here is 9, is 8. Okay, here is here, is here, is here, is here, is here, is here. Okay, 6 here, 8 here. 9 here. Here is 10, sorry. 8, 10 here. So on, okay. So you have the, so you have a, you don't see 1. The number 1 is, where is number 1? because you take a 3 and you take a minus 2, that is equal to 1, but 1 is not belong to 2z and 3z. It's not. 1 is not here. And minus 1 is not, also is not in the union. Many, so 2z is not a submodule of ZZ. Okay? But now you take a 2z and plus 3z. What is this? The conclusion is z. Why? Because 3 in z minus 3 in 3z minus 2 in 2z here. So this will follow is belong to 2z plus 3z. And that is equal to 1. 1 is belong to here, so 2 is here. 3, 4, 5, 6, 7, 8, 9, 10 is belong to. And so on. 0 minus 1 here is minus 2. 1 is belong to here, so all is belong to here. So that is equal to z here. So you can see 2z and union with 3z, and then you take the generated, that is equal to 2z plus 3z, and that is equal to z. Okay, that is one example. You can see the number here, and then that is very clear that the union is not a submodule. However, if you take the sum, it will be the submodule, and the generated of the union here is equal to example about the sum. That is the union and the sum. The second is the equation. So in our books, I can take the example here. The MR, the M3R, which R is the ring with identity. I always to say that the R is a ring with 1. Ring with 1. That is equal to the R, and then R, and then R. If you want to write the element, so that is equal to the A11, A12, A13, A21, A22, A23, and A31, A32, A33, and Ij is in R, A from 1 to 3, and J is 1, 2, 3. Okay, you can write this or you can write this. That is Ra, mean that the element here is in R. Okay. Now I will take the n is equal to the element, but the the between is a 0. So that is, you can write that is equal to the A110, A13, A210, A23, and A310, A33, and I say is in R. And it can prove that is the submodule of M3R. But now here is, I consider that is here. Okay, you can check this one easily because you can check easily. You remember that is, there are two that is MRR, okay, M3R, and this guy and this guy. But in this case, I consider this one. You remember that always you should ask here or here. It's different. But in this case, I use this one. For the module, that is very complicated because that is over what? Over R or over MR. In this case, I consider the R. So you can okay. Okay, so you can easily to check that the MR 3 is over R. Okay, and then in this case, you take the M over N. M over N is the element is this element is A11 0 A31 and A21 0 A32 A310 A33 and then plus N for every A say is in R, and then that you can check the element N here. So N is here. So when you plus this and this one, that is equal to what is that here is only here. So that is equal to 0, A1, 2, A3, 1, and then sorry, here is 0, and here is A22, and here is 0, and here is A3 0, and here is A32, and 0 plus N. Okay, why this is equal? Because you can write something like this. Okay, I will write here, and then yeah, okay. Because you write A110, A31, and then A210, A23, and here is A310, A33, and then you minus 0, A21, 0, A22, 0, and here is 0, A33, 320, that is equal to, okay, you write that is A11, A12 minus, and here is A31, and here is A12, here is minus A22, and here is A23, and here is A31, and then here is minus A32, and then here is A33. That is belong to n. So you can take it that is minus, here is belong to n. So there is, you can, this one, for example, I take it as x is y, so x plus n is equal to the y plus n. So the conclusion here is the Quotient submodule of m, here is m3 r over n, m3r over n here. Okay, that is the Quotient module of m over n is here. Okay, so I have give you two examples. One is about the union and sum, and the second is the Quotient submodule of the module R. So I finish the the section 2 here, and then remember to do the homeworks, and remember that before studying in the next next week, you remember send me the homeworks, the section 1 and the section 2 in Tuesday. Okay, so in Tuesday, and if we have the time, sometime I will correct some homeworks. Now I will transfer to the section 3, that is the module homomorphism. The module homomorphism. Now let's you have the MR and then NR. Two rights are module. And you take the F is from M to N. Is a map from M to N. So F is called, we have the definition here. F is called array R module homomorphism. Array R module homomorphism. If F preserve operation. Two operation. I say preserving two operation here is very important because people on way to say about the formulas. However, I emphasize the preservation is the preserve. Okay, I forget as here. The preserve is very important. Because the preserve here is related to the preserve the structure here. So I emphasize preserve and I provide you the formulas later. Okay, so here, so mean that the f of x plus y is equal to the fx plus fy. For every x and y is in M, and fx r is equal to the fx and r out for every x in M and for every r in R. You remember that is the first operation here is a plus here, and the second operation is point here, mean that the multiplication here, and then here is point here. Okay, so I would like to emphasize preservation, and here is formulas. Why I emphasize preservation and then here, because the reason is here. I would like to say more detail about this, but because that is very important, very, very important. Okay. So you can see, okay, I can draw here and then you can see the preservation here. Okay, here is M and here is N. And then you take an element X and Y here. Okay, X and Y. And the F is from M to N here. So what is F? X, and then you receive the Fx here. It's okay? And Y, you receive the Fy here. But in M, you have the X plus Y is something here. And you receive the Fx plus Y. But you have the Fx here and Fy here, and then of course you will have the Fx plus Fy. The problem is equal or not? And if preserve the sum, the addition, so the Fx plus Y is equal to the Fx plus Fy. Should be equal to. So you can see, you can add in the left and then we transfer to the right. That is the same. You transfer to the right and you take the addition. That is the same. That is very important. Preserve. That is very important. I can say some Vietnamese about this. Ok, ở đây là người ta hay sử dụng cái công thức là nói rằng một đồng cấu nó là như thế, nhưng mà cái ý nghĩa của nó là cái bảo toàn phép toán, đúng không? Bảo toàn hai phép toán. Cái phép dưới thì rồi các anh chị cũng sẽ làm tương tự. Tôi chỉ giải thích cái phép cộng cho nó kỹ thôi. Và như vậy thì các anh chị lấy một cái x và một cái y ở bên m, đúng không? Thì các anh chị cộng lại là được x cộng y ngay. thì cái gì chuyển sang bên kia nó sẽ là fx này, chuyển sang bên kia sẽ là fi này, rồi chuyển sang bên kia nó sẽ là f cộng y này. Nhưng ngoài ra vì có phân tử fx, vì có phân tử fi ở trong n thì là có phân tử fx cộng fi, thì như vậy là vẫn nhau, tức là nó phải bảo toàn cái phép cộng ở bên này qua bên kia. Và ta có thể nói một cái câu mà nó có vẻ là cái đầy đủ ý nghĩa của cái bảo toàn này là gì? Nếu chúng ta cộng bên này rồi chuyển sang thì cũng giống như chuyển sang bên kia rồi cộng thôi. Nào, cái câu đó là câu rõ ràng là mình cộng bên nào được, cộng bên này rồi mình chuyển sang, hay là mình chuyển sang bên kia rồi mình cộng. Chuyển sang ở đây là ý nghĩa của cái mapping, có nghĩa là cái ảnh xạ đó. Đây các anh chị hiểu ý nghĩa. Và tôi nhấn mạnh cái chữ preserving là vì sau này nó bảo toàn hai phép toán thì nó sẽ dẫn đến bảo toàn cấu trúc, tức là bảo toàn mô đun con, bảo toàn phần tử nghịch đảo, phần tử đối, vân vân, bảo toàn phần tử không, tất cả, tức là không bên này qua không bên kia, phần tử đối bên này thì qua bên kia lấy phần tử đối, vân vân. Cấu trúc mô đun con bên này là mô đun con bên kia, nghịch ảnh của mô đun con bên kia là nó sẽ mô đun con bên này. Như vậy nó gọi là bảo toàn thuật toán, dẫn đến bảo toàn các cái cấu trúc là như vậy. Cho nên gì là tôi nhấn mạnh cái preservation là vì vậy. And two formula here can be only right, that is only one formulas, that is f xr plus y s is equal to the fx and then r here plus fy and s here for every x y is in m and for every r s in r. Only you can, when you have the homework or you check something, you can only for the short doing for the briefly you can use only one formulas, but I would like to emphasize because that is the plus and then also the multiplication, so I say that the preserve two operation. Okay, that is very important because that is two operation. Okay, so now we have a many example and also we say the definition here. Okay, we say that we have the definition here. The homomorphism, if you plus what is here is injective, you will have the definition of monomorphism. If the f is homo and then plus b no not bijective, that is injective, that is what is succession. Toàn ảnh đúng không? Đây là đơn ảnh. It will be epimorphism. In Vietnamese, we say that the toàn cấu. And in Vietnamese, that is called it đơn cấu. And then plus bijective. Bijective means that the injective plus succession. We say that the we say that the the isomorphism. Isomorphism. The isomorphism. So you remember that here is when you have the here is if the map you have this one, and in Vietnam me that is called this đơn ảnh, toàn ảnh, song ảnh. But here is if you take with the homomorphism, then it will be called the monomorphism, epimorphism, and isomorphism. Okay. So now I will give many examples about this. That is example, and then we will use later. Many times we will use this. For example, the first, if you give the M and N, and then you take something like this, from M to N, and then all M, you take a 0, and then you will say that that is 0. Zero homomorphism. From M to N, but all M is 0. For example, M here, N here, and here is a 0 of N. Here is a 0 of M. And then all M I give is 0 here. It's a 0. The inclusion. The second is you can check the condition of homomorphism. Inclusion. Inclusion means that you take the N is the submodule of M, and then you have the inclusion here is N to M. And then on N here, you take N. Okay, so that is inclusion. Mean that here is, you can draw that is M here, and then N here. Okay, and 0 is here. And then you inclusion M to N. Inclusion here. Mean that the N here is also to take N. So the N is, mean that to inclusion to M. Okay, N is the submodule of M. We say that the inclusion. The first is, of course, the inclusion is monomorphism. Okay, the monomorphism. This is not mono, not epi, not iso. But you have the identity. Mean that you have the MR, and then you can write that identity M from M. All M here, you take M. That is isomorphism. You can write that is here, or sometimes people also say that 1. 1M. The same. You can write 1M, or you can write it M. It means that identity here. Okay, đồng nhất. The identity. Okay. We continue this. Now the example for M, R, and when I fix one M in M, and then I will say that the Fm from R to M, and then you take a R here, and then it will be M is a fixed M. Fixed M. And then you take the Fm from R to M, and then we can check that is homomorphic, because the Fm and then R plus R prime, that is equal to the M R plus R prime, and then that is equal to the MR plus MR prime, and then that is equal to the FMR plus FMR prime. And then Fm here is R, and then R prime here, that is equal to M R and then R prime. No, MR, sorry. And then that is equal to, okay, here. That is equal to the M and then R and then R prime to the M R prime here, and then that is equal to the Fm R prime. Okay, so homomorphic. You have the homomorphic because I can check here. But if you want to the FR, I say the hard HR, sorry. The HR from M to M, and then here is M, and then you receive with MR here. R is commutative. If you want the HR here is homomorphic, you should assume that the commutative, because you write the HRM plus M prime is easy. Is equal to the MR plus M prime R, that is equal to the HRM plus HR M prime is easy. However, the commutative is here. The commutative is, okay, I can erase here. You can take the H R, and then here is M R prime. That is equal to what is? Here is equal to the here M, and then to tie R here, M R prime, and then R prime R here. But you take the H R M and then R prime here. That is equal to the MR and then R prime here, and then is equal to the MR R prime, and here is equal to the MR prime R. So if you want to, this one is equal to this one, same as the first day I say to you. So should be commutative. Okay, the commutative, so this is equal, and so that is equal. So if you want to homomorphic, you should give the condition here is commutative. So HR is homomorphic. And one example is, the last one is for M, and then N is the submodule of MR, and then you take the M over N, and then you take the P from M to M over N for every M to M plus N. Okay. That is epimorphism. That is epimorphism. And we will call this natural or canonical projection. We will say that the canonical projection. You remember that is inclusion from N to M, and then N here is we say that the canonical inclusion. And here is for the submodule, we will say that the inclusion, but the Quotient, we will say that the canonical projection. Projection. Canonical projection. Here's a canonical inclusion. But these two important homomorphisms in module. So I think that I will stop the lesson here. And okay. Any question or comment?
Yeah.
Okay.
Yeah.
You can take the question. Minh.
Dạ, hay là ở cái định nghĩa của cái đồng cấu vành đồng cấu module này hay là cái FA1 cộng A2 này là bằng FA1 cộng với F của A2, thì cái cộng mà bên trong mặt này là cái cộng của, nếu mà là module là đồng cấu từ A đến B thì cái cộng bên trong cái mặt là sẽ là cái cộng của A, còn cái cộng bên ngoài là cái cộng của B, đúng rồi.
Yes, đúng rồi.
Vậy
rất đúng.
Còn ví dụ như là cái F của A nhân R này thì cái bên trong mặt là
phép nhân module của A,
qua bên ngoài là phép nhân module của B, đúng rồi.
Đúng rồi. Vì thế cho nên người ta gọi là bảo toàn phép toán là về, tức là mình cộng bên này qua bên kia là cộng bên kia, hai phép cộng nó khác nhau. Đúng. Mình rất là phân biệt như vậy là rất là giỏi. Phép cộng nó hoàn toàn khác nhau. Ok, đó là hai phép cộng, một phép cộng ở bên A, một phép cộng ở bên B. Bên dưới này là phép nhân module ở bên A, bên kia là phép nhân module bên B. Nhưng mà khi mà nó là đồng cấu thì nó bắt buộc phải bảo toàn, có nghĩa là bên này cộng bên này với nhau. Ok, bên này.
Yeah.
Any question or comment more? Okay, if you have not any question, we will stop here and see you next week. Okay, maybe 1 week's online studying, and then it can be open to directly studying or not, I don't know. Okay, but in the information from the college, it will be 1 week studying online, but okay.
Yeah.
So we stop here. We leave the meeting now. Okay. Bye bye.